Hi guys, last time we did an analysis for a bar under tensile load. Today we are going to look at a beam under flexural load. So the problem statement we are going to do is something of this sort. We are keeping the geometry and materials as well as the loads similar to the previous case, but today rather than having in tensile, it will be flexural load acting out of plane. For that case, we are going to use beam element, and because now we have a shear load acting here, it will cause bending in the beam and the stresses will be generated due to the bending. Usually we have this stress is equal to m by I because of the moment creation. So I have done quick calculation and we will be expecting somewhere around 3000 megapascal at fixed end of the beam. Let's go to Abaqus module and see if we get similar value or not. So first thing first, we will make a beam. Our problem is going to be 2D planar. Base feature we are going to use is wire. Under wire we will be later on choosing beam elements. We will write a Python script in next video so that we don't have to do all these small work again and again. Let's give the dimensions to this beam 500 mm. Our beam is ready. Now next step we will create material, again steel, mechanical property elastic isotropic material, yes, 200,000 megapascal, 0.28 Poisson ratio. Material is defined. Now we'll create a section. What kind of section today we want to make is steel beam section, right? So here if you're using solid elements or solid brick elements, you'll be using solid, but today, or else if you're using a shell elements, then you will probably go for shell elements, but we are using a wire element, so beam. And under type, last time we had chosen truss, but today we are going for beam. Yes. So here we need to define this profile for the beam. Click here on the profile icon, beam profile. Let's call it square profile. Here we have a couple of options: box, rectangular. Usually box, pipe, ILT, these are for thin wall sections, and circular, rectangular, hexagonal, trapezoidal, these are for solid sections. We are going for rectangular, and then we can make the dimensions here. Here two dimensions are there, A and B. A is 100 cross 100 in our case. Please have a look first and second direction because this will be helpful to understand when we give the orientation. Section Poisson ratio 0.288. We are using steel, and okay, we have created the section. Let's assign this section to our part. Done. Okay, dismiss. Turn to green. Our part has material assigned to it. Let's quickly mesh this part. Under meshing, first thing we will do is let's give 15 global size, and I want you to have a look at element type. Last time we had given family truss because it was a bar under tensile load. Today we are going for beam, and we are using linear order elements rather than quadratic to avoid the computational time. One can always go for as per their need. So let's quickly mesh the part. Cool, the part is meshed. One beautiful thing here about I would like to show you guys is you can always go for view option. Under view option, you can go for part display options, and you can render beam profile if you want to have a look what exactly is the section you have given. Apply. Okay, did not work. All right, anyway, we'll check this some other time. Not sure why it not work. Usually it works. Okay, we'll go for the next thing. We'll get back to this part later. Let's go for assembly and bring our part here, beam. Now we'll see under step what kind of analysis we want to do. We want to do static, nonlinear geometry. We are not bothering. It's okay for our case. So step is defined. Under that, we will go for loads now. We have a concentrated force acting at right hand of this beam. Choose the right point. Under global coordinate system in second direction, we want to apply minus 1000 kilonewton. Minus because y is in positive direction. You can always change the sign and see where exactly or which direction it is applying. Apart from this, only thing pending now is boundary condition. Let's go for encastered boundary condition. Done. Encaster. Okay. Dismiss. Our part is ready for the analysis. Now let's quickly make a job for it. Beam, beam, one. Let's call it beam one. Let's reduce the memory size to avoid hanging of the system and quickly. Okay, what we missed here is we forgot to define the orientation, which I was mentioning in while property section, first and second direction. So here we have to define the orientation for the beam. Each cross section will take the orientation according. So here these arrows are depicting this is the tangent direction, and the first direction as we were looking earlier, that was as per this system it is going to be in z direction, so that is okay. We can see minus z direction 1 2, and this is the tangent direction. Each cross section is defined in first and second plane, 1 and 2 plane. Okay, so okay, this is why we were not able to see the view option. Yeah, because we had not defined the all inputs required at that time. Okay, let's just quickly go for the analysis now. Submit the job is submitted. Soon it will start running. If there is no error, if there is any error, it will show up an error. Meanwhile we'll just have a look what exactly we are expecting. So in this problem we are applying a shear load, so because of that there will be bending throughout the length of the bar and throughout the length of the beam, so let's call it as beam, and at that stress will be generated due to the bending alone. There is no in-plane load acting here, so all the stress is going to come is through the bending stress. Let's see if the job is done. Job is done. Let's look at the number, and we are expecting 3000 megapascal. Interestingly, we have reached to 2955. Let's have a look at this one. Yeah, so the value is coming around somewhere around 3000 megapascal, very close value as we were expecting from the theoretical value. So hope this clarifies. Thank you.